Hi everyone, this is Kalyan Kumar this side and welcome back to Chemistry Universe. This is the second and the last part of ethers, and in this one we're going to discuss the physical and chemical properties of ethers. So let's get on with the video. Alright, here we go. So this is the physical and chemical properties. First let's just look at the physical properties. Now most of them are quite generic statements. We know that lower ethers are going to have less van der Waals forces. So they are gases, and the higher ones are liquids, but they are volatile liquids mainly because the forces are van der Waals, so they are not very strong forces. And ethers are definitely less polar than water, makes sense. No hydrogen bonding here. And therefore, which is why they are less soluble in water too. And the boiling point of ethers is obviously less than the corresponding alcohols, because remember, ethers and alcohols are functional isomers, and they have less boiling point because the hydrogen bonding is not there. So now let's look at the chemical properties. And the first one is called the salt formation. Now, salt formation means when ethers are treated with cold, concentrated inorganic acids, they form oxonium salts. And the reaction between ether and an acid is like a Lewis acid base type of interaction. Say, for example, you have this and you add HCl to it. So what the O will do is it will pick up the proton and it will form what is called as oxonium ion. So this particular stuff is oxonium ion and it is oxonium chloride. So this is what happens when you treat it with cold concentrated HCl. The same happens with sulfuric acid. You will get the hydrosulfate ion and oxonium salt. Now, at this stage, what you need to understand is, and this will come up later, but I would like to ensure that we talk about this right now, and that is that if you want to know whether a particular acid is going to form a salt or probably react further, because remember, ethers are extremely sensitive to acids, and this is one of the reasons, because ethers O have a lone pair and they would love to have a proton. So they would like to behave as a Lewis base and there's a proton available. So remember, ethers are sensitive to acids, number one. Number two, with cold acids, they don't break, they just form salts. But that too only with HCl and sulfuric acid. When it comes to cold HBr and HI, remember Br minus and I minus are better nucleophiles than Cl minus. So what happens is that after forming the oxonium salt, so let's say you have this oxonium salt being formed. Now what will happen is that the Br minus or the I minus would now also act as a nucleophile because they are better nucleophiles. And there is a good leaving group, O plus. So they will attack one of the R's, that is, let's say Br minus here. It will attack one of the R's and one of this bond will break and you will end up getting an alcohol and RBr, R prime Br. So one of the alkyl group gets attacked and the other turns into an alcohol. And this is the product when you use cold HBr and cold HI. Now the question comes, which R does it attack? Well, this is the way it goes. If out of R and R prime, one has high tendency to show SN1 and the other has high tendency to show SN2, then SN1 is the bond that breaks. So say for example, R prime is SN1 and R is SN2, this bond will always break. The SN1 is the one that wins the attack of Br minus. So this bond breaks immediately, you get a carbocation and then you have Br minus attacking it. Now if instead of one showing SN1, the other showing SN2, let's say both of them are capable of showing SN1, which means I'll have SN1 and SN1, then the higher SN1 wins. So that bond will break. But then since both of them have SN1 tendency, you will get the other product also, but that would be less. But the fact of the matter is that is not going to give you a good yield of any product anyway. But if both of them do show SN1 and you make only one product, then go for the one where the CO bond breaks from the one which shows greater SN1, not the lesser SN1. Okay. So the lesser SN1 becomes alcohol and the higher SN1 becomes the alkyl halide. Now what happens is, if both show only SN2, which means both cannot, I mean, if they're symmetrical, it doesn't matter. If they're unsymmetrical, if both show SN2, one definitely will show SN2 more than the other, less steric hindrance. Perhaps, there are groups in it that can help with SN2, like the withdrawing groups, etc. So suppose one of them shows more SN2 than the other, then the greater SN2 wins. Now, this may again be a little bit of a contrary to what I'm saying, because when I said SN1 and SN2, I said SN1 is the one that will be preferred. And here I'm saying SN2 is the one that is being preferred. But remember, what happens is that if SN1, if one shows SN1, the other shows SN2, the SN1 will not wait for the nucleophile to attack. It will immediately break to give a carbocation. So that is the one which will definitely have the Br or the I. If both show SN2, then the Br minus will tend to attack obviously that carbon which has higher tendency to show SN2, because both cannot show SN1. So the bond does not break before the nucleophile attacks. So the nucleophile has to attack and only then the bond will break. For the nucleophile to attack, it will look for the one where hindrance is less. And obviously, wherever SN2 is better, it will attack there first. So the one that shows greater SN2 becomes the RBr or R prime Br or whatever, and the other becomes the alcohol. So this would come up soon. So I thought I'll just tell you this before. Reaction with oxygen. Now, generally, ethers react with oxygen in two ways. One in the presence of ozone and the other in the absence of ozone. We are more interested in the second part, because the second part is the one that actually is useful to us in the lab. In the first part, what happens is it will react with an oxygen atom. And remember, ozone is present. So this lone pair of O, now remember, there is a lone pair here, and this oxygen requires two bonds or two electrons to complete the octet. Remember, oxygen atom always requires two electrons to complete the octet. It will form a coordinate bond. The lone pair will form a coordinate bond. Okay. But this is not that important. The important thing is the second one. In the second one, if you take an ether and you treat it with oxygen gas, you will find something like this. It's called an ether hydroperoxide. So basically what is happening is the H from here is going to one of the O's, and that the other O is getting attached to the carbon. Oxygen is like this. So just remove this and put two dots, and just imagine one dot getting an H dot from here and forming OH, and the other O dot forms a bond with C dot, and you get ether hydroperoxide. But of course, we'll have to look into the mechanism because it's a free radical reaction. So that there will be an initiation step, a propagation step. So the initiation step is this. You have the ether reacting with oxygen. And as I said, the pi bond of oxygen breaks, both O becomes dot, and one of the O dots takes an H dot, and that will be always the alpha carbon, this carbon. Because remember, the H dot, when it takes, it will form a radical here. And this radical is stabilized by the lone pair. Now, if you remember GOC, there I've told you that an unpaired electron can be stabilized by a lone pair. So here what happens is that it takes an H, alpha H, and then it forms this. Now, one might feel that they are going to join themselves. Well, that's not the way it happens, because remember, the chain initiation step does not happen for all molecules at the same time. In the chain initiation step, you'll have to give something, some energy in the form of heat or sunlight. So if I give sunlight and then I give only a little amount of photons, so which means I'll only get a little amount of this and a little amount of this, and lot of this and lot of this are floating around. So to expect these two to meet is going to be very difficult. The chances of these two meeting are greater. So in the initiation step, you will get these two radicals. Now what happens is comes the propagation step. Now in the propagation step, this primary alpha radical will react with oxygen molecule, which is an excess of course. Again it breaks the pi bond of oxygen and takes one of the oxygens and makes the other oxygen as a radical. Now this will meet the other excess reagent, which is the ether. It will take an alpha H from this, convert that into an alpha radical. And that way, the propagation step can keep going on. Now, but one cautious thing, and the reason this is important, this reaction is because ether hydroperoxides are highly explosive. They're solids and they explode on slightest heating or rubbing. And since ethers is always used as a solvent, you'll always have a problem. So before you use an ether sample, you must make sure that you take a tiny sample from this and test it out whether it has this ether peroxide or not. And the way we test it is this. So ethers have to be always tested for hydroperoxides before using in any reaction, as heating may cause explosion. So the ether peroxide is reacted with an Fe2 plus salt. So the ether peroxide will get reduced and the Fe2 plus gets oxidized to 3 plus. And Fe3 plus can be easily tested by the use of KSCN. Remember, only ether peroxides will react with Fe2 plus, not ethers. So once Fe3S is formed, Fe3 plus, it's react with KSCN, it forms a red color. This is a red color complex. That confirms the presence of ether peroxide. So either you don't use it or you find some particular way of converting the peroxide into the ether again. Now, but then you want to prevent also this from happening. You don't want an ether to become an ether peroxide. So you have to avoid both air and sunlight. So you store in air-free dark bottles. The next is the reaction with PCl5 and SOCl2. Now this is something which we have already done in when we were doing the reaction with PCl5 and alkyl halides. So when you react with PCl5, you know that it will cut off both bonds of O and it will give two Cls to each of the two atoms. So it will form, so you will break it from this R and O, then R prime O will break. The two P and Cl bond breaks and the Cls get attached to the Rs. You will get RCl, R prime Cl, and you will get POCl3. This is one of the ways of producing alkyl halides. And the same thing will happen with SOCl2. This bond breaks, then this bond breaks, then this breaks, and they all join and you get SO2. Now, the nature of RCl and R prime Cl. Obviously, when you have metameric ethers, you know metamers. So ethers show metamerism. They are a bivalent functional group. So if you want to distinguish between two metamers, the best way to do this reaction. Now, obviously, since in metamers, both sides will be different in both ethers. So what will happen is that you will get different types of alkyl halides. So the combination of RCl and R prime Cl in two metameric ethers will be different. And testing them would tell us that they are metamers, that these ethers were metamers. So these reactions can be used to distinguish between metameric ethers, as they would give different combination of alkyl halides. And we can even, the reaction with PCl5 can be used to distinguish alcohols from ethers also. PCl5 is something that can be used even for distinguishing alcohols and ethers. And one way of doing that is, of course, you can test for acidic H, but then on top of that, you have this also reaction where PCl5 will react. Again, the O, both bonds will break. You'll get RCl, you'll get POCl3, and you'll get HCl. HCl is a gas. And HCl can be easily tested by bringing a rod dipped in ammonia. It gives you dense white fumes of NH4Cl. Then comes reaction with HX, and this is the one I was talking to you about. So we already did with cold concentrated HCl, the reaction leads to the formation of oxonium salts. And this was the reaction. But with cold HBr and HI, the reaction leads to the formation of an alcohol and an alkyl halide. And I already told you how you get that. So oxonium salt and you get alcohol and alkyl halide. And as I said, alkyl halide will form, if it is SN1 and SN2, SN1 is preferred. 2 SN1s, better SN1 is preferred. 2 SN2s, better SN2 is preferred. Now, alkyl halide is formed for that alkyl group which leads to a more stable carbocation. That is if both are SN1. But if you to use hot, as I said, both will become alkyl halide. So it doesn't really matter which one is attacked first. Because you get this, you'll first get alcohol and alkyl halide. Another molecule of HBr will react with the alcohol. And remember, alcohols react with HX. So they release water and they'll form alkyl halide. So you will get this and this with water. Now let's check out some examples. You have this particular ether and you're using cold concentrated HI. What do you think will be the product? Pause the video, make the product. Again, you want to check out where the I is going to attack. I will attack where SN1 or SN2. Now the right one can show both SN1 and SN2. It is benzylic. The left one can only show SN2. So from the perspective of SN1 and SN2, the right one wins. The right one should get the I. Whereas if you look at SN2 also, the right one has better SN2 than the left one. So even from the point of view of that, the right one should get the I. So the left one will become the alcohol and the right one will become the I. What do you think will happen to this one? Pause the video. Make the product and then check. Now obviously here, both of them cannot form a carbocation. So both of them will show SN2. Which one do you think will show a better SN2? The right one. Because the right one has lesser hindrance. So you will get the left alcohol and the right alkyl halide. So what do you think will happen with this one? Pause the video. Well, remember, the benzene ring will never get attacked. Nucleophilic substitution on benzene ring is very difficult. You need nitro groups all over to make it go through ARSN2. So it's not going to happen. So what will happen though is that the I- will attack this guy and you'll get phenol. So you are going to get ethyl iodide and phenol. Then comes reaction with Cl2. Now Cl2 reacts just like it would react with alkanes. Only difference being it will show free radical reaction with ethers, but it only attacks the alpha carbon. Now molecular chlorine reacts with saturated compounds like alkanes to give substitution products in sunlight that we know. But if the radical formed is stabilized by resonance, then the reaction even occurs in dark. So for ethers to attack on the alpha carbon, you don't need even sunlight for halogenation. It is of course substitution. Ethers undergo chlorination or bromination at the alpha position in dark. So you have this ether and I put one equivalent of Cl2 and it is a dark medium. So what do you think will happen? Obviously it will take an alpha H and form a Cl there. The other Cl will go with the H. So don't think that if there is a Cl2, both H will go. The H will also need something to go with, right? This is called alpha chlorodiethyl ether. Now comes the question, what happens when I have two equivalents? Because now you can either have the same carbon attacked twice or the different carbons attacked. Well, if let's say one of the alpha carbon doesn't have an H, only the other one does, then we know the obvious choice. But if both of them have, like in this case, what will happen is you'll get this. Why? Because once a chlorine is already sitting, this radical, if this H goes, if this radical is formed and there is no Cl here and this radical forms, this is more stable because here you have a minus I effect of Cl. So it is the other carbon which will show. But what happens when you have excess? And then you have sunlight also. Now, if you have simply have excess in dark, 4H will go. But if you have sunlight also, all of them will go. It's called perchlorodiethyl ether. And in this, what would you suggest? Which radical do you think is more stable? The right or the left? Obviously, the right. Then comes combustion. Now, combustion is pretty simple. It is a standard combustion. But they are highly inflammable liquids, so you make sure that they never expose to direct flame. So you have ether and oxygen. It's a typical combustion reaction. It will form CO2 and water. Then you have reaction with BCl3. Remember, BCl3 is a Lewis acid. Now what happens is 3 mole of the ether and 1 mole of BCl and BCl3, if they react, what will happen is these 3 Cls will go with 3 of this. Remember, even though I'm writing 3 of ether, there are actually 6 ethyl groups because there is 2 in 1. So 3 would make 6. So 3 of the ethyls will take 3 of the Cls, and the other 3 ethoxides will go with boron. So you will get this. And if you want to check out the mechanism, well, this is how it happens. You have the ether, you have BCl3, Lewis acid base reaction, and you will get this. Now this helps remove one Cl. And after the Cl is removed, you will get this, and that Cl will attack one of the carbon atoms. Again, the same rule is applied, SN1, SN2, and this bond will break, and you will get one ethoxide on B and one ethyl chloride. And the same thing will happen with the other 3 also. Then comes reaction with acid chloride. Now, ethers react with acid chloride to form esters. They'll react with anhydrous AlCl3 and zinc chloride or zinc chloride, and you'll get esters and alkyl halide. Again, you have to figure out which ester is formed, because ultimately you have to figure out, is this OR coming onto this carbon or OR prime coming onto this carbon? Because this is going to stay as it is. Which OR comes depends on, again, the nature. So we need to check the mechanism again. So to know that, what we do is, we say, okay, let's check out the mechanism. We have the acid chloride. AlCl3 will obviously form an acylium ion. Now, this would attack, the ether will attack as a nucleophile on the electrophilic acylium ion, and you'll get this. Now what happens is, the base Cl minus, the AlCl4 minus, removes the Cl minus. That will attack one of the R. And this bond will break. So which R will it attack? It follows the same rule. If both show SN1, higher SN1. One SN1, the other SN2, SN1. Both SN2, better SN2. So that will become the halide and the other will form the ester. Then comes reaction with carbon monoxide. Again, this forms an ester. And again, we have to find out that if this CO is getting attached, what is happening is the CO is getting in between this R and this O. There's a CO coming in between them to form an ester. So again, we have to find out between which alkyl group and O will the CO come, which we can only know if you know the mechanism. And this is the mechanism. You have the ether, BF3, obviously you know why it is used. And now the CO has C minus, which will act as a nucleophile. It will attack one of the R. And this bond will break. So which R will it attack? Same rule. You get this and this. Again, you get an acylium ion. And now you'll find this breaking and this O attaching, and you'll get this. So which will be R and which is R prime? That is R which shows better SN1 or better SN2. And the other forms the OR. Then comes dehydration. Now ethers will undergo dehydration with concentrated sulfuric acid. If you remember when we did, I think it was alcohols, where we defined temperatures when this will happen. So what happens is it forms an alkene. Now how does it form an alkene? It's very simple. You will have ether forming first this oxonium ion, right? Now what will happen is the HSO4 minus will come and take this proton, and this will break and this will go here. So it will form an alkene of this one. Then again you have an alcohol with sulfuric acid again show dehydration, and it will give you alkene again. So now you have reduction. Now we have done this when we again did alkyl, I think it was preparation of alkanes. This was reacted with red phosphorus and HI, if you remember. And what HI does, it breaks all the bonds with oxygen and gives H to each. So you will get alkane and you will get H2O. Then you have oxidation. Now ethers will first react with KMnO4 and H plus, and since there is an acidic medium, they will immediately become the alcohol, and it's going to be a primary alcohol. But then this will, with KMnO4, it cannot remain as alcohol; it will form an acid. Then comes reaction with H3O plus. Again, we have done this. This is H3O plus. H plus attacks the O, and you get oxonium ion, and then eventually both will become alcohol. And again, the same logic, if carbocation is stable, then SN1 or else SN2. So let's check out some options here. One may say that if alcohol is formed in both, how does it matter in which one water attacks? Well, this is the reason. Because we need to know where the ether's O will go. So where do you think it will go? Once the O gets plus, where will the H2 attack? Obviously, both show SN2, better SN2. So CH3 will be attacked by water, which means CH3OH will not have the O18. It is the ethanol which will have. What about this one? Well, now one shows, the right one shows SN1, the left one shows SN2. SN1 is preferred. Water will attack the right one. The left one gets the 18 and the right one does not. And what do you think happens here? Obviously, nothing is going to ever attack pH, so the O18 will automatically go with phenol. Now, the last part is the preparation of epoxides, because they are very special ethers as they are cyclic, as well as the carbon-carbon bond still exists. So we've already done the preparation. I'm just going to recollect them from peroxides. In fact, we made ethers from alkenes even using peroxide as well as oxygen. But I'm not showing the oxygen, I'm just showing the peroxide part. Because here they would ask you which O of the peroxide, the peroxyacid will go. Will this oxygen form the ether, the epoxide, or will this oxygen form the epoxide? So it seems that based on the mechanism, it is the OHO which forms the epoxide. So you'll get this. And the mechanism we've already done in alkenes, just check that. Then you can even get it from vicinal halohydrins. You add first X2 and water. Then we know that halogen in water, one carbon will get OH, the other will get X. This is called a halohydrin. Now when you add OH minus, one might feel that the OH minus will attack the left carbon and remove the X. But instead of that, what it does, it removes this H as proton, makes this as O minus. This will attack the carbon and this will remove the X. Obviously, it will attack from the opposite side. But since it's a single bond, it can rotate. So you will find that it will form the epoxide. Now, if I were to give you a stereochemical example, there is a cis alkene. First I add this, then I do this. I want you to make the product with stereochemistry. Remember, epoxides can also have cis and trans because the two atoms on the carbon are different. They're Me and H. So pause the video now and make the product. This is what happens. Now, let's assume in the halohydrin, remember it's an anti-addition. So let's assume that OH attacked from top. The water attacked from top, which means the Me and the H go here. And let's say the Cl attacked from the bottom on the other. So there will be H and a Me here. And remember, this OH minus is going to take this H and convert that into O minus. But remember, the O minus will attack this carbon to remove the Cl only when it is opposite. That means only when it is like this. If the single bond rotates and the O minus comes down, it's not going to attack anymore. It has to wait for it to go up. So the attack happens from the top. So this will attack this carbon and the Cl will grow. Can you see the two Me's are still together and the two H are still together on the same side? So the product would be a cis product. Now let's quickly look at the chemical properties of ethers. Now, there is a ring opening in basic medium. This is unique for epoxides. Only epoxides can open up the ring in basic medium. So what happens is the epoxide reacts with some kind of a nucleophile and then you add water. Now remember, KSET means K plus and S minus, ETS minus, just like ETO minus. Now, obviously it will only attack, since it will attack and then the bond will break, it is going to be an SN2 type. So on which carbon will the SN2 type occur? On the right carbon. So this will attack here and this will break and that will get the H and you will get this. So try this. We've already done this in fact. Again the R- will attack the right carbon, pure SN2. Try this. Again the D- will attack the right carbon. Now let's look at the acidic medium ring opening. Well, you have the epoxide. Let's say you add HBr. So don't you think the first H will come here? Now remember SN2 with SN1 character, because of the plus, the bond will start breaking and this bond is likely to break more because the positive charge on this carbon, being a secondary carbon, is more stable. So this bond will start weakening and this end up getting more delta plus and the Br minus will attack that carbon and therefore the Br comes in the middle. Try this. Same logic. O becomes plus, water attacks the middle carbon, the O18 goes on the right. What do you think will happen here? We have done this actually. Now AlCl3 will behave as the acid. So you will have the AlCl3 here. This will be the plus. Where will the CH3 minus attack? It will attack the middle carbon and this will break. So you will find this forming. And that concludes the physical and chemical properties of ethers. So that's the end of part 2 of ethers. I hope you were able to learn something in this. Watch it as many times as you want. Make sure you make notes while watching it. And with that, this is Kalyan Kumar signing off. Have a great day and thank you for watching this.